All right. Hey, folks. Happy Monday. Hope everyone had a nice weekend. Just kicking us off here. If you have any issues with audio or video freezing up, past two streams, we had some issues with audio, which I think have been all sorted out at this point. Um, and the stream before that, we had some issues with the camera freezing up, and then also um, the CamLink stream of my dev machine messing up. And so, if I hit either of those, feel free to drop something in the chat, and we'll get it addressed. Also, if you haven't already, feel free to jump in the chat and get some conversation going. Definitely always welcome feedback, input, etc. While we're working on stuff, or questions as well. Definitely more than happy to go through some side quests on these streams. They're very free form, as folks know who have been here before. But with that, let's go ahead and I'll get switched over here to the main stream. All right, so it should be coming through. Today, there's a few different things that we're going to work on. So primary thing that I dropped in the description and also put on social media, etc., is working on instruction decoding for RV64I, which is the RISC-V 64-bit integer instructions. And I've got the spec open here that we're going to be taking a look at. And I did a little bit of prep here to get some of this set up for instruction decoding, but haven't done too much of it, and we'll kind of talk through that. So that's, I guess, kind of priority one, that we'll see if that is the first thing we work on. So I'll go ahead and note that down. RV64I instruction decoding. So that can be our primary thing. Other two things that are on my mind today is continuing blog post from last week. So for folks who were here last week, thanks for being here. But we were working on a blog post, how are LUTs use as storage elements on an FPGA. I would like to get that posted tomorrow, if possible. We ran into some side quests, you might say. Honestly, I just got pretty distracted throughout it, trying to find some more information. But we do have some content here, and should be able to potentially wrap that up. Depending on how many folks are here, I might prioritize that and then circle back around to the instruction decoding. Other things here. Let's see, continuing blog post. Oh, and then, oops. The third thing is create create and document Verilog test bench. So one of the things that you may notice if you check out the MOS repo is we have these simulation sources. So like our register file here, they're written in C++. They're using Verilator, which is basically a tool that converts your Verilog into C++ and then allows you to write tests for it. And that's great. The issue with that is that if you want to run it in something like Vivado, at least to my knowledge, that's not possible. So I guess it's nice for open source tool chains, which we'd like to get to eventually using, but right now we've been spending a lot of time with Vivado, and the Verilog test benches kind of work nicely there. And so I'm thinking we'll probably take kind of like a two-pronged strategy, having both simulation and Verilator, so supporting that simulation at least, and then also having Verilog simulation as well. So that's kind of the big picture here. Also, I was going to see if I could invert the colors here. Dark mode. There we go. I think that's a little nicer on the stream. Okay. Cool. So, talking about instruction decoding first, maybe. Basically, at the beginning of a 5-stage pipeline for a processor, let's just kind of draw 5 stages here. So broadly have fetch, decode, execute, memory, access, and write back. It's probably 2 words. We have some of this outlined in the blog post I wrote a few weeks ago on this register file. Yeah, fetch, decode, execute, memory access, write back. So it's hyphenated. That's what it is. All right, write back. Cool. Okay, so basically we have to get the instructions from memory. So where would be the best place to put this? Well, actually, let's go ahead and just connect these up here. All right. So fetch, we're going to, oh, that's going to be way too big. Let's just do it down here. Get next instruction from memory. And then here we're going to decode instruction, which is what we're going to be focusing on today. Then over here, we are going to execute the instruction, which may involve memory access in the next stage. Actually, what I'm kind of going off based on here is textbook Computer Organization and Design, RISC-V edition. But execute is typically involving the ALU, or typically that's considered the execute phase. Let me see if I can find a good example here. I think they split it up at some point. Yeah, so it could be performing an arithmetic operation, or it could be calculating the address that you're going to use for the memory access. Yeah, it might be helpful to draw this out at some point for folks to be able to see. But anyway, we're going to be focusing on the decode today. So decode instruction, execute, let's just say arithmetic operations. Memory access is pretty straightforward. Access main memory, which is, potentially could be cache, right? This could be a misnomer. And then since we're using a register kind of processor here, we are going to be updating a register potentially based on that. So update, we'll say destination register. So let's kind of stay in this single cycle mode. So kind of sticking to this blog post here a little bit. And so if we're thinking in this vein, basically we have to, in the decode step, think about control signals that are coming off of this, right? So based on the instruction, which instructions are always going to be in RISC-V 32 bits, we have to basically take those bits and decode them and think about the signals that we need to send through the rest of the pipeline here to be able to determine, right? So in hardware, everything is executing all the time. So this, write back circuit, for example, is always present. But if we don't have a destination register, then we're obviously not going to be writing back. So let's with that in mind, let's jump back over here. And these are kind of the signals that we're going to need to be driving based on the instruction that we get. So maybe we should pull up the spec here. And like I said before, we're going to be using the RV64I base integer instruction set, which basically builds on the RV32I instruction set. So as we're going through this, I want to, split this and go over to docs and make an instruction set document here. MOS instruction set architecture. MOS uses the RV64I let's see, the RISC-V 64-bit integer instruction set architecture, and we'll say that's RV64I as its base instruction set. I say, how did that turn into a 3? All right. So let's just go ahead and document that. So for RV32I, unprivileged state for the base integer ISA for RV32I, the 32X registers. Okay, so first thing to think about is X length describes the X length is it's not instruction length, it's kind of like the data width, I guess you might say. So like the instructions are always 32 bits, even with RV128, but the registers are going to have are going to be different widths. So for instance, we'll have X length equals 34. So we'll have 32, sorry, did I say 34? 64. We'll have 32 64-bit wide registers. X length is the width of, maybe they actually have a formal definition. Introduction. Maximum, okay, here, perfect. RISC-V ISA has fixed length 32-bit instruction that must be naturally aligned on 32-bit boundaries. Yeah, and then we can talk about 16-bit instruction parcels here, which is embedded if you're using RV32E. Okay, so we'll say I length is max instruction length, or width, we should say, I think. Oh, they use length. We'll say length. Which would make sense since we're saying I, len. All right. Where do we first bring up X length? here we go. Use the term x length to refer to the width of an integer register in bits. Integer register width. Registers only supports 64-bit, or sorry, 32-bit instructions. Equals 64. And here we'll say I length equals 32. All right. So important part here, provides a convenient ISA and software toolchain skeleton around which more customized processor ISAs can be built, which is kind of what we plan to do long term with MOS here. Four base ISAs in RISC-V are treated as distinct base ISAs. Common question is, why is there not a single ISA, and in particular, why is RV32I not a strict subset of RV64I? Some earlier ISA designs, SPARC MIPS, adopted a strict superset policy when increasing address space size to support running existing 32-bit binaries on 64-bit hardware. The main advantage of explicitly separating base ISAs is that each base ISA can be optimized for its needs without requiring to support all the operations needed for other base ISAs. For example, RV64I can omit instructions and CSRs that are only needed to cope with the narrower registers in RV32I. The RV32I variants can use encoding space otherwise reserved for instructions only required by wider address space variants. Let's see. So this talks about like a disadvantage being that if you have hardware that needs to emulate, for instance, RV32I on RV64I, then that's going to be more complicated, which makes sense, right? Because if it was just a strict subset, then you could, like, imagine you had something that looked like this, and you said, this is my RV64I processor, and it's made up of, handling. This isn't, one for one, right? Because it's not just like every instruction is the same amount of required hardware or logic. But let's say, like, this handles 8 instructions, this handles 8 instructions, et cetera, et cetera. And if RV32I was just, these 16 instructions here, then you could, in theory, just use the same hardware over again. So we do lose that, but for our purposes, that's not really super critical. Yeah, we'll leave the add alone for now. Memory, a RISC-V heart has a single byte addressable space of 2 to the x length bytes for all memory accesses. Maybe we should go ahead and start just a section on memory. Heart is a hardware thread. That's not really a memory specific thing, though. What I want to get down here is that we're going to have 2 to the x length bytes for all memory accesses. But we can go ahead and say word 32 bits, 4 bytes, half word 16 bits, 4 bytes, half word 16 bits, 2 bytes, and then double word. It's going to be 64 bits, 8 bytes. Whoa. All right. Looks good. Check the comments here. See if there's anything. Nope. Still looks good. All right. Well, we'll say quad word also. Also, double word is 1 word. 1 0. Whoops. Quad word 128 bits, 16 bytes. All right. Memory address space is circular so that the byte address. Okay. Accordingly, memory address computation is done by the hardware. Ignore overflow and instead wrap around modulo 2 to the x length. Hearts have a byte addressable address space of 2 to the x length bytes. Execution environment determines the mapping of hardware resource into a Heart's address space. Different address ranges of a Heart's address space may 1 be vacant, or 2 contain main memory, or 3 contain 1 or more I/O devices. Reads and writes of I/O devices may have visible side effects, but accesses to main memory cannot. Although it is possible for the execution environment to call everything in a Heart's address space an I/O device, it is usually expected that some portion will be specified as main memory. Yeah, cool. When a RISC-V platform has multiple Hearts, the address space of any 2 Hearts may be entirely the same or entirely different, or may be partly different but sharing some subset of resources. And we're not going to talk about address translation quite yet. Okay, so this is interesting verbiage here. Each RISC-V machine instruction entails 1 or more memory accesses. So it's considering, an instruction, fetching the instruction, and then potentially performing a memory access as 2 separate things. And so having to fetch an instruction is always at least 1 memory access there. Beyond instruction fetch. The execution environment determines what portions of the non-vacant address space are accessible for each kind of memory access. Okay, yeah. And I've written a little bit about RISC-V weak memory ordering, which always helps my mind get into a pretzel. But we should talk about it sometime. So if folks are interested in that, let me know. Also, it looks like that the webcam froze up, so that's great. Properties. Integrated webcam. Okay. Truly don't know why that happens, but it should be coming back here. It's back on OBS. It should be back on the stream here in just a minute. Okay. Base RISC-V ISA has fixed 32-bit instructions and must be naturally aligned on 32-bit boundaries. Okay. And like I said, we're not going to be talking about the E extension here. So we're only going to be talking about 32-bit instructions. Okay. I align. Instruction address alignment constraint the implementation enforces. Instruction address alignment constraint MOS uses 32-bit alignment. So I align equals 32. All right, we'll skip over this tentative expanded instruction length encoding for now. We'll skip instructions that cause traps, unspecified behavior. All right, base instruction set. RB32I contains 40 unique instructions, though a simple implementation might cover the call e-break instructions with a single system hardware instruction that always traps and might be able to implement the fence instruction as a not reducing base instruction count to 38 total. All right, we are going to be using RV64I. But it basically builds on the RV32. So this is only talking about the differences. So yeah, x length equals 64. Most integer computational instructions operate on x length bit values. Additional instruction variants are provided to manipulate 32-bit values in RV64I, indicated by a W suffix to the opcode. These W instructions ignore the upper 32 bits of their inputs and always produce 32-bit signed values. Okay, yeah, so it's just ignoring the top part. Okay, so I think we should go through the RV32I instruction set and then come back to it. Also, it looks like the camera is messed up again. I do not know what the issue is here. Properties. Huh. Switching it back to leave unchanged seems to have fixed it. All right, back again. Okay, so R-type, I-type, S-type, U-type, and then we also have B-type and J-type. So these are the formats that we're going to be dealing with here. So let's go ahead and note that down here in the docs. So RISU. Core, or let's see, instruction formats R I S and U. And then we also have the B and J types, which are basically variants of S and U. B and J. Gosh, my typing is all messy today. Also, if we want to look at some visualization, privilege levels, introduction to instruction formats, this is what we want here. So this goes through and breaks them down. So that's helpful. Register ALU instructions is R. ALU immediate instructions and load instructions. Looks like camera's still holding up for now. Nope, that is not what I want. Store instructions, comparison, and branch instructions. We'll combine these. J. Store instructions, comparison, and branch instructions. Store instructions, comparison, and branch instructions. And then jump instructions, jump and link instructions. Okay, so we're mostly going to be concerned about opcode here. But let's keep reading through these. B and J are immediate encoding variants of S and U, respectively. So immediates here are basically just saying we're going to provide the value in the instruction itself. So if we give you 32 bits, right, of an instruction, so let's say we have our instruction here, and it has, 1, 1, 0, whatever you want here. So these could tell you, hey, do something, right? Or it could say this part, well, that's actually what it does. This part is telling you, what we're trying to do. It tells you how to decode the rest of it. And then some portion of this could be like, hey, this is where you go get the value that I want to use for part of this operation. And let's say this is where I want you to write the result of the operation. This is an address. And then this part could be an operation itself. A value itself, right? So this could be the value. You could say one of the values is in this address. We want to write to this address, and this is a value itself, just included in the instruction encoding. So that's how the immediates kind of work here. So an I-type instruction, let's see, what did we say I-type is used for? ALU immediate instructions. So in R-type, we are going to say, hey, there is, let's say it's an add instruction. We are going to say, hey, this is the address of the first register. This is the address or the number of the second register. And then this is the register we want to write to. So we'll add the values stored at these locations and write the result to this location. However, in I type, maybe we'd say add I or addy or whatever you want to call it, add immediate. We might say this is the source of the first instruction, and then here is a value. Here's the lower 12 bits of a value here, and we're going to add that to the value in this register and then write it to this one. Okay. 12-bit immediate field used to encode branch offsets and multiples of 2 in the B format. Okay, yeah, it's just talking about how these immediates are decoded. So that the 20-bit immediate is shifted left by 12 bits to form U immediates and by 1 bit to form J immediates. All right, integer computational instructions. I kind of wish these were organized by format, honestly. Well, maybe let's reorganize them by format, or see if I already did that maybe in this blog post. I did not. I just gave examples of each. Okay. Oops. Our format instructions. So these are going to be register, register, and load. All right. We have add. Func7 and func3 fields. Select the type of operation. Okay, I want to jump down here because one of the things I can't remember is, So like if we have R-type, we might have different opcodes for R-type instructions. But for example, all of those instructions we were just looking at have the same opcode. And maybe that's actually kind of like a decent way to organize them. Yeah, I kind of like that. I think other R-type instructions. So like load. These are the additional RV32I. Where is our load instruction? Store word. Okay, load. So they have a different opcode. Wait. Oh no, sorry, it's just register ALU instructions. All have the same opcode, which is 0110011. Operation determined by funct3 and funct7. So we can just take those and say add I guess we're just kind of copying the spec, so maybe this isn't super productive. And honestly, so I think one of the important things here is 1, 2, 3, 4, 5, 6, 7, is that all we really do in instruction decode is check the opcode, because these are going to determine, well, maybe just as a starting point, these are the signals that we're going to set from the opcode. So are we going to branch? Do we need to do a memory read? Do we need to fetch a, do we need to write back from memory to register? So are we going to write back at all? Is this an ALU operation? And mem write. Are we going to write to memory? What's the source for the ALU? And are we going to write to a register? Actually, I'm not sure. I pulled these off of the diagram I was just talking about. Let me see if I can grab the page. So maybe we can also talk about control signals. I guess we'll just call it architecture. the opcode of each instruction indicates, or let's see, determines whether each of, let's see, 1, 2, 3, 4, 5, 6, 7, whether each of the 7 control signals are driven high or low. So let's maybe talk about the control signals. So we have branch, we have, part of this might be that I didn't document this well. Decode, branch, we have mem read, we have mem to reg, we have ALU op, mem write, ALU source, reg write. Okay. All right, it has a really nice table here, actually talking about each of them. So although it doesn't actually talk about branch, but I think it's pretty self-explanatory. We can see. Yeah, so I think it's whether we take the branch or not. Yeah. Oh, so it's basically going into an AND function. So we're saying, is this a branch instruction, and is the comparison 1? If so, then branch. Let's see. If this is a branch if this is a branch instruction and the result of the comparison is 1, branch. But really the control signal is, that's not really right. It's high if instruction could result in branch. If high and the result of the comparison is 1, then branch. Okay. Memory read. High if instruction specifies a memory address to read. I guess these are kind of self-explanatory. Or actually, mem to reg is interesting. High if the value to be written to RD comes from memory. Low if it comes from ALU operation. I'm looking at the ALU control here, and I'm also seeing that the webcam is frozen again. That seemed to have fixed it. All right. So the ALU op is determines what ALU instruction we perform. So these are all 1-bit except for ALU op, which is 2. And I'm going to explain here in just a second what it means. Well, in theory, assuming the camera is working. Yeah, it looks like it is. Two-bit, 1-bit, 1-bit, 1-bit. Okay, so ALU op is saying, here I can just read it. For our type instruction is set to indicate that the ALU control should be generated from the funct fields, except for, so ALU, if it's 1, 0, we're saying use the funct3 and funct7 fields to use the funct7 and funct3 fields to determine what operation to perform. And then for like a load or a store, our ALU op, there's 0, 0. And that means perform address calculation. So don't consider funct3 and funct7. That makes sense. And then it gives another example, which is break if not equal. So I know the camera is also frozen again. All right, we're going to switch to the not what I want it to be, but it seems to be working better. View. Properties. Well, that doesn't look great, but we'll try it. Sorry, 1 second. Okay, that seems to be at least a little bit better. At least this is coming through, which is what we want. Okay, so what we're seeing here is, let's say this is our processor, our functional diagram. And if we have our ALU and then we have an ALU control, we'll make it smaller. And then we have our decode unit up here. Decode. We have 2 bits. Let me make these coming out of here that are coming in and saying what to do. And then we also have information about the funct3 and funct7 coming in here. And then they tell the ALU what to do based on the inputs that it has coming in. So the examples that it gives are just all our format instructions and load word, store word, and break if equal. And in these, the ALU op examples are 1, 0, and then these are both 0, 0. So calculate address. And then break if equal is 1, 0. Sorry, I had those backwards. 0, 1. So in the break if equal case, we're actually setting it to subtract. That's a little strange, though. So it looks like my camera still appears frozen on the stream, but it's fixed. I'm just going to leave it as is for now, and we'll deal with it later if needed. Okay. So the ALU control should be generated from the funct fields. Right. Okay. So maybe a way to summarize this. Our format, well, let's just say this. 1.0 means that we should use funct fields to determine operation. For other instruction formats, we don't have funct fields, so we need to tell the ALU what, or really the ALU control, right? When you tell the ALU control what to do explicitly. So we have basically a truth table here where we're going to say that we have two signals coming in, ALU1 and ALU2. We'll just draw an abbreviated one here. 1, 0, use funct, 0, 0, address calc, and 0, 1, I'm going to say subtract, because the subtraction is used for comparison. I should like save these notes for people to have afterwards if needed, even though they are super messy. It might be nice to follow along. I guess you can also just pause the video. But what I want to do is kind of like take this information and for each instruction, say what we're going to need. Okay. That was a bit of a side quest there. Mem write. ALU source is high if the second operand is immediate, low if second operand is from register. So that'd be RS2 in that case. Okay, register write. High if the if RD should be written back to. I need to clean that up. That one's interesting though, because that's kind of what we talked about here. This write control, that's actually exactly what that is, the reg file, because it's saying that, hey, at the next positive edge of the clock, so if we do something like this, I'll draw a couple cycles here. Okay. So rising edge of the clock. So we have a rising edge here, and we have a rising edge here. And between these 2 points, this is a cycle. And so you can imagine that we're doing, fetch, decode, execute, memory access, write back. And then when we get to here, we should have a value that's present in data, right? Data should be populated with the value, whatever it came from. It could be an ALU, add of 2 register sources. It could be a load from memory or anything like that. And then right here, if reg write, we note that down? Yeah, reg write, for example. Let's see. Reg write is high. Write to RD. Okay, cool. So let's jump back over here into the ISA. I mean, I think this is really useful if you actually talk about the signals here. I guess I haven't really seen this from other sources, including this book, and it gets kind of confusing for me. So we're going to be doing it. Hopefully it's useful to someone. So for each of these, we're going to say branch, memread, mem to reg, ALU op, mem write, ALU source, reg write. I'm just going to duplicate this so once we start populating it, we'll have another here. Or maybe we should actually just do a general kind of like instruction template. Add. Well, we can copy it later. Funct3, funct7. So in that case, for all of these R format ones, we're going to be saying that branch memread 0, mem to reg 0, ALU op is going to be 0, 0. Oops. For some reason I'm landing on the wrong key today. Okay, memwrite, high infrastructure writes to memory. No, it doesn't, because we have, for all of these, right, we have a registered destination specified. So 0, ALU source is going to be 0. Reg write is going to be 1. So let me check that. I think that we have an actual add in this book here. Well, actually, so I have, so ALU op 1. Oh, sorry. We said it's 1, 0 for use funct signals. So we're going to have like the same for all yeah, so we could probably just put this up here. Maybe obvious. It's helpful for me to go through it. Yeah, you know, I feel like it's useful to have it repeated. Maybe that's silly, but I think it's can be useful. Subtract the value in RS2 from the value in RS1, and that's it. Next step. Yeah, let's put this over here. Add, subtract. Get rid of this. Make it a little bigger. Okay, SLL. So I know SLT is set larger than. Let's see, can I get an always on top here? Cool. Nope, that's still sub. SLL 0, 1. Can't see it. Hold on. Shift left. Set less than immediate. Logical shift left. Ah, shoot. To RD. All right. Let's. Where is my. Oh, I can never forget how to. Oh, there we go. SLL. And SLT is 1, 0. So I'm gonna replace signals with control signals. All right, cool. Hey, Daniel, thanks for jumping in here. Also, thanks again for the audio help was that last stream or the one before? Either way, I appreciate it. Anyway, I'm just going through and documenting these instructions and the control signals they correspond to in the processor. So pretty tedious, honestly, but it's helpful nonetheless. All right, this is making this smaller is not really working super well for me. Okay, set less than SLT signed writing 1 to RD if RS1 is less than RS2, 0 otherwise. Nice. I need to get rid of this always on top. Why won't it let me undo that? There we go. It's weird that it doesn't let you full screen. All right. compare, let's see, perform a signed comparison of RS1 and RS2 if RS1 if RS1 is less than RS2, write 1 to RD, otherwise write 0 to RD. All right, sounds good. What do we have next? I'm going to pull this back up. Oh, nice. Daniel, you're able to make it to Open Source Firmware Conference. I am so jealous. Are you doing the, are you getting to do the Oxide tour? I know that was like a pre-conference event. I really wanted to go. Unfortunately, my talk didn't get accepted, but just getting some details from the same inspector to finish up my slides for tomorrow. Oh, yeah, I know. Your talk looks awesome. Super jealous I'm not going to be there. Nice, doing the field trip. Awesome. I'll have to get a report back from you. All right. SLTU. So that's going to be 1-1 on the func 3 and perform an unsigned comparison. All right. Let's see. We have Zor. We'll post about it on X. Sounds good. Well, I hope you have a great time. That's super exciting. I know there's going to be a lot of really cool people there. I will say I am going to be able to go to Hackaday SuperCon. I don't know if you've ever been to that one, but a few of my coworkers actually started the conference, and they're awesome, as one would expect. And so yeah, I'm extremely pumped for that, and that's in about a month. Heard about it on the Amp Hour. Awesome. Chris actually, well, I guess maybe I shouldn't say that on the stream, but I get to hang out with Chris a lot, which is awesome. Let's see, Zor, SRL, which SRL is going to be just like SLL, except for we're going to be shifting right. Oops. Oh, did I double up the SLT? I guess so. Oh, nice. Met Chris at Embedded World. Yeah, he is awesome. What did I just copy? Okay, whatever. We'll take that. X. So, looks like you're about to say something, Daniel. Can you just copy instead of typing manually? Yes, I can. I can. I have been modifying them slightly as I've been going along, and I'm obviously adding the control signals. The format, I could probably let it be a little closer to what they have there. But yeah, I'm just copying right now because I'm going through it anyway. And the specific instructions. So like that sentence I just wrote is not actually in there. Only the I think SLL one. So I'm making slight modifications, but yes, it is very tedious. It's kind of helped me commit it to memory too. So to each their own, I guess. Control signals, SRA 101, and this one should be 101. And this one is 101. Actually, as a note, when I started out, I hadn't committed to. I hadn't realized or had the realization yet that all the control signals were going to be the same for our format. Then that obviously quickly became apparent to me. So right now this is pretty tedious, and the other ones, the control signals are going to vary a little bit more. SRA. Yeah, arithmetic shift rate. By the amount held, I should say, in the lower 5 bits of RS2. Not held in also, I'll say logical shift for these to make it appear. No, this one's arithmetic though. Arithmetic. All right. So we're almost through all of the. So we have OR and AND left. Cool. And they're going to be the same description pretty much as the XOR, but with different Func3 and Func7, of course. 110 and 111. All right. So that was tedious, but let's move on to I instructions, which will also be tedious. So I format instructions are going to have lots of the immediates. So if we jump back up here, we can see ALU immediate instructions and load instructions. So a lot of variants of what we just had. But we are going to have some different control signals coming through. So let's look at some of the examples here. So these are, that didn't really work. These ones here are all going to be, all these load instructions are going to be I format, and then all of these immediate here are going to be I format. And so let's point out maybe one of the things that could be missed, I guess, if you're not looking at this. Like looking at a holistic view of all the instructions is if we look at and immediate and I, we've got this 111 opcode, right? Or sorry, 111 funct3 here. And that's going to match the non-immediate encoding variant here. So we have and with 111 and funct7 of all zeros. And then we have a different instruction format. What this means is that if we see the 111 funct3 here, then we can know that we're performing an AND operation. So in the ALU control, what we were talking about earlier, we have this 2-bit signal going to the, maybe I'll pull up the XColor here. We have this 2-bit signal coming into the ALU control. So if we say that it's 1, 0, then we can then look at the information coming in here from funct3 and funct7 and say, hey, is funct3 equal to 111, right? And if so, then we can say, hey, you're performing an add operation here. And interestingly, or maybe not, but we're only varying the 30th bit in the instruction for all of the funct7s here. So we actually only need to send in here, this wire is 4 bits wide here. So we're sending in the 3 bits of funct3 and then 1 bit of funct7. I'm just going to note that down because I think that could be something that I lose sight of. Funct3 encodings will match their, let's say, funct3 values will match their immediate encoding counterpart. Only the only bit 6 of funct7 is varied. So the remaining bits can be disregarded. So these are the kind of things that I look at and, you know, probably should just be able to notice from the beginning. But it's actually really helpful to me to look at this and say, oh, yeah, I can see here after copying all of these down that we only need to consider this one bit. I also have a diagram, right, that has it, but it's not really clicking for me until I'm actually going through these instructions and getting a sense of it. Okay, so for all of the immediate arithmetic operations, we're once again going to have the same control signals. Well, no, not. We will have the same control signals for all of them, but I think that we have one that differs here. For so, what do we call these in the spec? Base instruction formats. Register immediate instructions. We'll call them AOU immediate. We'll just add this here. Register AOU instructions. Add immediate is going to be our first one. And there is no funct7 in these. We only have funct3. And we can say that it matches add, so we could just, it should be 0, 0, 0. Add the sign extended 12-bit immediate to register 1. All right, add immediate. Check the video again, make sure it's come through. Looks like it. Okay, so set less than immediate. So these are all going to be pretty similar. Oh, let me take a look at our control signals here. So our AOU source is going to change. Yeah, so AOU source should be 1 here. Funct3 matches instructions register counter part. AOU source control signal is set to 1 for all. The other type we have here is load instructions, right? Oh, I guess maybe we should put that after these. What does register immediate mean? First of all, hey Crystal, thanks for joining. Immediate means that I was actually talking about this earlier. If you need to go back in the earlier replay. But immediate, this is where we're talking about it, is basically like you have an instruction, right? And in the instruction, you can encode really whatever you want in it. But in RISC-V, we have an opcode, and then we have these different formats that are going to specify different things. So, for example, we're looking at these R format instructions, which is all of, well, let me copy them, but is from add down to and here. And they all have the same opcode, and they have RD, RS1, RS2, and also Func3 and Func7. And these are all basically saying, hey, this is the operation to perform, or they're saying this is the register where a value that I want to use in the operation exists. The alternative to saying, here's the register, or here's the address of something, is saying, here's the value itself. So you could either tell me, hey, use the value in register 7, and in register 7, there could be the value 100. Or you could just say, hey, use the value 100 and encode that in the instruction itself, right? If there's enough bits to represent something, then you can just put it right in the instruction. So that's what the immediate variants of these are doing. So instead of saying, hey, add the value in RS1 and RS2 and store it in RD, it's saying, hey, add the value that I'm giving you to RS1 and store that in RD. And we also mentioned just a minute ago that the Func3 values are going to match their counterpart in the register examples. So SLTI is the next one. You really just basically copy and paste sign extended 12-bit immediate for RS2 here. And Func3, we could just go back, see SLT Func3 is 010. It's also going to be 010 here. Cool. Looks like that answered the question. SLTI, let me just double check on that one here. SLTI set less than immediate places the value 1 in register RD if register RS1 is less than the sign extended immediate when both are treated as signed numbers, else 0 is written to RD. SLTIU, that's kind of interesting. The immediate is for sign extended to X length bits, then treated as an unsigned number. So I'm going to note this down here. What was it? Add I RD RS10. RDRS1 pseudo instruction. All right. SLTIU 011. Sorry. Oops. That was sloppy. Move this down here. And we'll go ahead and copy all these down. 100. 100. And then it was Ori and Andy, I think. I think this one was 110. No. This one, forgot to update that one. This is 111, which matches and, which I should know. All right, looks good. We'll jump back up here just to make sure. So yeah, Zori RDRS1 -1 performs bitwise logical inversion of register RS1. Nice. Zori RD RS1 -1. Yeah, so it'd just be flipping all the bits. Juice implement the not. Cool. Ori is going to be the same. All right, and then let's at least get through the load instructions here. And the control signals are going to be interesting for the load instructions. Oh, also, I should note the opcode. For all of the ones we were just looking at. And this should make sense, right? For the same opcode, the control signal should always be the same. So I can probably pull those up there later if we need. But not for the same format, right? So that checks out. Opcode. And then I'm going to take just one of these and we'll modify it here in just a second. For the control signals, funct3 000 for LB. Let me make sure I don't have something on the hour here. All right, I've got a couple more minutes here. So for these, we are going to need the branch is 0, memread is going to be 1, right? We do want to read. Mem to register is going to be 1. ALU source is 1, right? Because we still have the immediate. So that matches the register immediate ones. Reg write is also 1. So memread, memwrite. And then ALU op is going to be 0, 0, though. So we're saying 0, 0, telling that we just need to add, I believe. So branch 0, memread 1, right? We need to read the value from memory. Memory to register 1. yeah, memory to register 1, ALU up 0, 0, memory write 0. We're not writing anything to memory, we're just loading from memory. ALU source 1, we're saying it's from use the immediate, and then register write. Okay, cool, makes sense. Load and store instructions. Source copy. Oh, okay, we're just looking. All right. Let's just go ahead and grab all of those. So we have load byte, load half word, load word, load byte upper, load half word upper, I think. Okay, and we also have some extra. Is this the same opcode? No, it's not. The opcode for the 32-bit. Or the immediates from the, yeah, okay, so we added another 1 there, 0, 1, 1. No, 0, 0, sorry, 1 after, 0, 0, 1, 1. There we go. So this compared to 0, 0, 1, 0, 0, 0, 0, 1, 1, 0, 1, 1. Okay. So we really need Ori, Andy. We also need the 64-bit variants. We need those for register as well as register immediate. I wonder if they have a specific name for those. To do 64-bit. All right. We'll go ahead and copy these for now since we've been doing it. Load byte. We have a couple more. more of these. LB, LH, LW, LBU, LHU. All right, and let's get those opcodes right before we wrap up here. 000001. LW was a 010. Yeah. 010 100 101. 010 100 101. Oops. Probably need to hide that from my doc while I'm doing this. Let's just make sure I got that. 100 101. All right. I feel like we got some good notes there. We didn't get to work much on the actual decoder, which we have over here. I have gone in and labeled a bunch of these opcodes already, though. Some of them I don't think we're going to need. So we have load FP. So we just went through some of those loads right there. And if we look at the opcodes here, they're all going to start with 1-1. And that's true also when we add in RV64I. That's just true across the board, I think. Yeah, across the board. And so, yeah, RV32. So like looking at our loads there, it's all zeros. So if we look at our opcode load, then we just have 5 zeros. That's all we need to consider flowing into our decode here. And I noted that, so opcode load. So for example, if we wanted to actually just do this for the I format, let's see, where do we do load byte? The control signals are always the same. So we can jump over here and we could say branch equals 0. Actually, these are, well, no, sorry, we're not clocked here. Branch equals 0. Reg write mem read equals 1. Mem to reg equals 1. ALU op equals 0, 0. Mem write equals 0. And ALU source equals 1. And then reg write equals 1. So we're basically just doing that for the various opcodes that we support. And then we should be able to write a test bench that just verifies those outputs there. And I'm going to go ahead and maybe just to round us out here, I'll create a test bench that we'll work on next time. Sorry, touch decode testbench.v. All right. Cool. So we'll stick with that for now. One of the things I want to kind of like examine is this might be somewhat of a silly thing to say, but like a lot of this, I feel like that when I'm just looking at it here, I'll switch over to the fuller view. A lot of it, it feels like when I'm just looking at it, that I just like the solution is like think really hard about it, right? And a lot of times, sometimes that is the case. That's just how you solve the problem. But sometimes there's some techniques and strategies you can use. So one of the things I would like to do is maybe get some folks who have worked in this space, right, and maybe worked on some of these specs on the stream and be able to talk to them a little bit about this. But I do hope that folks who are tuning in get something out of this. I'll push up this PR with just some of the drafts in there, and then we'll continue to build it out. As always, if this was helpful or if there's a way it can be more helpful for you, feel free to reach out to me. I think all of the socials are linked on my YouTube channel page. But yeah, it's always a lot of fun to do this, and I appreciate folks who come join and ask questions or provide feedback. So everyone, I hope you have a great week. I'll probably stream again at some point this week. But until then, have a good one.